everything, I looked at this problem, which is, what is that, 10, 9B, something like that. 10B, yeah. And everybody got it wrong. I'm like, oh, I need to go over this. No, everybody got it right. The book has it wrong. So I'm still gonna just kind of review it, but y'all did good. You got it right. The book got it wrong. So when you work through this problem, I'll just talk my way through it. But in the end, the answer for one of the transfers inertias is to the 9th, and the other one, the whole, is to the 6th. And the book treated them both to the 9th. So they got a dramatically different number, like huge difference from what we got. So I guess it's something to watch for. Also, I think this one was even, so maybe the answer wasn't in the back, but just because you're different than the back of the book doesn't mean the book can be wrong. It's not wrong very often, but it's definitely wrong. They got the same numbers that we got for the transferred inertia, and then the answer is wrong. So I'm guessing that's what they did, is just forgot the 10 to the 9th part. So anyway, be careful with that. So just a reminder, when you get a problem like this that's not symmetrical, you've got to find Y bar. You've got to find that location of the centroid. So probably the problems here on out, they're going to give that to us just because they're going to want us to focus on the stresses. But now and then I'll just give you either on a quiz or on the midterm, probably for sure you'll have one of these. So just remember, if it's not symmetrical, you've got to find that neutral axis before you transfer the inertias to figure out the inertia before you go for bending stress. Okay. I'll always give you a hint on that, especially if something's going back to the first chapter we did and now it's week 4. The problem will say, remember, find that composite centroid before you start. All right. So I did that here, just using Y bar, area times X's, area times X's, and I subtracted the whole. And then divided by the area. And again, you subtract the area down here. 294, 525, just below the 300. So the big rectangle was 300. And since we're removing mass above, it will shift it down, right? If all that was removed above, then it would be way down here, type of thing. So the bigger the removal, the lower it'll shift that centroid. So try to give it a guess before you do it, then you'll know if you're at least going in the right direction. Okay, and then after I do that, I always determine my transfer distances because you're going to need that in that transfer formula. So this transfer distance for the big rectangle was 5.5 millimeters. And this transfer distance for the whole, to the red here, was 125.47. So that's what you need out of finding this neutral axis. You got to have those transfer distances. Once you have that, then you're set up to transfer the inertia and come up with a transferred inertia. So that should be the original. So here's the original base height over 12 for the big rectangle. Then that plugs in here, and then you have area times d squared. Give me that to the 9. Big number. So then I find the inertia of the circle just in its position. And I always put a little 2 on it, like origin 2. Then that plugs into here. And then area d squared gives me that. And it was to the 6th. So they had these 2 numbers in the solution manual. And then they came up with, oh, sorry. They had these 2 numbers in the solutions, but then they came up with like 1.34 to the 9th. I'm like, what? How could that be? Anyway, that's what I got. you guys were in that region, depending on how much accuracy you carried through. Okay, and that's good enough. You know, like I said before, we're not going to be working anywhere near the failure mark. So we're always going to have a factor of safety on this thing. So just carry 3-4 places when you calculate it, and it'll work out good. So just in perspective, right? This is like, this number here is like a billion, right? To the 9th. And then we're going to subtract like a million from a billion. So it doesn't change this number much. It went from 5.4 to 5.2 to the 9th. So subtracting this from this doesn't change it much. It seems like it should, but it's to the 9th is such a giant number. It's like taking 1 away from 1,000. It's not going to change it much, right? Still pretty close to 1,000. All right. Good. I might give you a few more of these just as extra practice because they do get tricky. Was there any others that were perplexing to you that you did out of there? You did the one with the structural shape, right? Yeah. That one? How'd that go? Rectangles. Found Y bar first, correct? Yeah, you had to, right? So locate that XX axis. They're drawing it in for you there, right? But you got to locate that first, and then you know the transfer distance, and then you know the transfer distance. Transfer distance doesn't matter whether it's positive or negative because you're squaring it in the transfer formula. So doesn't matter whether your distance is kind of from here down to here or from here up to here. That doesn't matter. Because here's the neutral axis of that upper shape. Here's the neutral axis of the lower shape. So here's this transfer distance, and here's this transfer distance. Like once you get those, then you're able to transfer everything out. What do you think? Need me to work it or negative? Positive or negative? Okay, let's do it. That's fine. Everyone can just suffer away. That's what I say. I don't want to leave it because we're going to leave it behind. I don't want to leave it behind until we got it, or at least we think we have it. So this is on page 173. It's number 9. Maybe it should be out further. Something like that. And we're 2 inches, 10 inches, 2, 12, 14 across the bottom. Is that correct? Yeah. All right, so I'm just going to label them right away, 1 and 2, and I'm going to go for Y bar. And I'll set my axis, right? I'll set my axis here. So this is Y and this is X. And if we're going for Y bar, we're really just working up and down, right? The location of this X axis. It looks like it's symmetrical about this axis, right? So we don't have to do that one. We know where it's at. So Y bar is going to locate the X neutral axis. So area of 1 looks to be 20. Is it inches? Yeah. So 10 times 2, right? And then the y distance from my axis is going to be 2 plus 5 is 7. And then I got to do the bottom one. So this formula, y bar equals the summation of a times y over the total area. That was the equation. So I've done the first area. Now I need to do the second area. Since it's a solid, I'm going to add it. That's 14 times 2, 28 for the area. And then the distance up to its centroid, 1 inch. All of that over the total area. So stop me if I got a number in there that you don't know where it came from. 3.5. So that is the composite neutral axis. Pretty low down here. That is the total area. So yeah, big A means total area. So that's 20 plus 28. I just did it in my head, 48. So now I need some transfer distances because I know I'm going to need the inertia and I know I'm going to need the transfer formula because the centroid of this one is up here and the centroid of this one is down here. And they are not at the red axis, so I have to transfer them. That's the rule. So I'm just going to write out the first one. And I'll just use the transfer formula right away and just fill it in as I go. So I know the inertia of a rectangle is base height cubed over 12. And that's what this first statement is, the inertia about its own axis. So the base is 2. The height is 10, just doing this shape. So the transfer formula that I'm using is that. And this inertia is the inertia about its own axis. And this inertia is the inertia about the composite axis. Area d squared. So I'm just filling it in. The area of shape 1 is 10 times 2, 20 inches squared. That's this A. And then the transfer distance is here. I'll call it D1. And this is where you got to figure it out. The way I do it is I go from the base to this axis is going to be 5 plus 2. So that's 7, right? And then up to this is 3.5. So I know it's 7 minus 3.5. Three and a half, right? 3.5 is 7. So 3.5 squared. Don't forget to square it. Super easy to forget to square it. And I would crunch that number. without verifying my number. That's what I got. Got some head nods, that's good. And then the second one, same game. Base height squared for this one, base is 14, height is 2. So that's the inertia about its own axis. And then I need its area, that was 28. And the transfer distance, which is here. So it's 3.5 minus the 1 down here. Should be 2.5. All right. Correction was made right here. I had that squared. So that generated new numbers there and there. All right, let's do one more. Did you do 32? No, let's do 32. Kind of as a practice. So I'll set it up, you set it up, and then we'll work it. You can start to work it, but then we'll work it together. All right, so I collected some information, drew my picture, collected some information. Got the area of the W shape, got the D dimension, which is the total height, 10.1. So even though it's called a 10, it's 10.1 tall. And then I got the inertia. And then for this C shape, I got its area because I'll need that. But I got the thickness of the web. That's this dimension. Because I'm going to need that. It's stacked on top. And to locate this thing, I actually looked up the distance from this back side to the centroid, and it's 0.698. Now, I think they call that X bar, but it's not something I would call it because it's a Y distance in my drawing, right? So I don't call it anything. I just put it in. You're going to need to know where that axis is, and it's 0.698 from the back, right? From this very top point. So then I looked up the inertia, but I looked up the Y inertia, right? Because that's the way it is in the book, even though I'm calling it an X because it's an X in my diagram, but I use the Y inertia. So that's the tricky part of these shapes. When they're out of position, you have to use the right information for your drawing, right? So that's why I use this 3.86 inches to the fourth. It's in its weak position, so that's why you use the smaller number. This one's in its strong position. So now I think I have everything to go for locating this Y bar. For that, you really just need the area and the Y distances, right? Because that formula, red shows up okay. Y bar equals the summation of AYs over total area. So if I do this W shape first, oh, here, I'll do the C shape first because I called it number 1. So I need the area of the C shape, that's 6.08. And then I need the Y distance. This is the tricky part. So what I need is that. So this is Y1. Okay. So the way I do it is I take the total distance of the W shape, which is 10.1, add to it the thickness of the web to get to the top, and then subtract the 0.698. That's how I do it. There's probably other ways to do it, but I say, okay, from bottom to very top is going to be D, this D 10.1 plus the thickness of the web, 0.282. That gets me to the top. And then I subtract this to get down to this distance. Okay. So I can write that over here. Y1 equals 10.1 plus 0.282 minus 0.698 to get Y1, which is what I need in here, Y1. That makes sense? All right, let me run it. What'd you get? I believe you. I get 9684. Decimal point in the wrong spot. 9.684, 9.684 inches. So that's area Y of 1, the C shape. It's all good. So then I got to do the other one, and it's a solid, so I'm going to add to it. I need the area of the W shape, 13.3. And then I need the Y distance to the W shape. That one's pretty easy. It's just half of 10.1. And then over the total area, which is going to be the 6.08 plus the 13.3. And then crunch it. $6.5038. Yep. Step 1 complete. So the other good news is when you calculate these things, they really help you with their transfer distances. Because now we know what Y bar is, 6.5038. We can go after transferring the C shape, and we can go after transferring the W shape because neither one of them are in the correct location. So I'll do the C shape first. So we need its inertia about its axis. So that's 3.86. We looked it up. And then we add to it the area times the D transfer distance squared. So I need the distance between this axis and this axis. So it's going to be, what is it going to be? We have Y1, right? 9.684. And if we subtract Y from it, we have the transfer distance, right? That makes sense? Yeah, you really need a good drawing, need it kind of big so you can kind of work your way through it. But it should be 9.684 minus 6.5038. Is that 3 point something? Yep. I'm just going to go 3.18 squared. $65.34. Anyone else get something like that? Oh, here. That's a plus. Yeah, this is summation. So that means add them together. A1 Y1 plus A2 Y2. Add. Yep, add them together. Yeah, no, that'll get huge. And if this was a whole, we would actually subtract it. Brian. Yeah. I don't know. Yeah, whatever you want. I'll be able to figure it out if you do it all in one line. I do them individually and then just add them. That helps me when you have holes and things like that to keep those negatives and positives straight. But yeah, either way. The 3.18 is the transfer distance. So that's from here to here, right? So I took Y1, which is all the way up, and I subtracted Y bar, and I was left with that. Yep, so it should be 9.684 minus 6.5038. And I try to kind of put those together. That makes it a little easier to figure it out rather than drawing one on one side of the drawing and one on the other side of the drawing. All right, so the second one, I need its inertia, 248 inches to the fourth. I need its area, 13.3. And I need its transfer distance, which is going to be right here. This is D2. So I know this distance is 5.05, half of the 10.1. And then I know this distance is Y bar. So it should be 5.05 from 6.5038. This is Y2. I get 145 squared. Yeah. So then we can crunch that out. $276.11. and add them together. Yep. I got 4, 5, but I did a lot of rounding.